Hey guys, this is Carl from University at Buffalo, and today I'm going to show you how to use Markov chain Monte Carlo to tackle some actual problems. So the general idea about Monte Carlo is that okay, so now let's dig into this notebook. We can skip those texts, and first thing first is to import libraries. You need to switch the TensorFlow version back to TensorFlow 1, and if you have issues with NumPy, you can always downgrade all those packages by the following command. And since it's on Google Colab, so don't worry about the environment in your local computer. And our first topic today is to get familiar with the Bayesian landscape. So we first just generate some normal distribution about x and y. So now let's dig into this notebook. We could skip those tags. And first thing first is to import the libraries. You need to switch the TensorFlow version back to TensorFlow 1. And if you have some issues with NumPy or other packages versions, you can use the following command to downgrade them. And since we are on the Google Colab now, so we don't need to worry about the changes in your local computer. And the first topic today is to get familiar with the Bayesian landscape. We first generate some uniform distributions on variables x and y, and here we can see it's basically a constant because it's uniform distribution, and both are from 0 to 5. And we can also visualize that in a 3D space, so that's the like a top surface of the space. And then if we instead use the exponential distributions for x and y, so now we can see it's not a constant anymore, but we have the highest probability at 0.00 and lowest at 5. That's due to the nature of exponential. And we can also see the top surface now is deformed, and we have a different probability depending on the position you're at. So that was just a quick example, but now we want to see what is the posterior look like by imposing a likelihood to our priors. So first, we have some ground truth parameters, that is 1 and 3, and then we use a Poisson distribution to generate our priors. And look what we have. We have a 2, 2, so unfortunately, that's not exactly the ground truth, but it's not too bad. It's still pretty close to that. And then we generate our likelihood that is shown by here. This means given our priors, then what is the probability to get our ground truth? So that's the likelihood. And then we multiply or we impose this to our priors. That is, the first case is our priors is given by a uniform distribution, and we literally just multiply a constant into our likelihood function. So this is the posterior. And for the second case, since we have exponential priors, then after multiply the likelihood, this is the posterior we have. And since we only generate one sample for this time, so it always looks kind of stupid. But if we use probably 10 or even better, 100 samples, then let's see what we get. Now, obviously that those posteriors are converging, which is a good sign. That means we are narrowing down our result. So now let's use the Monte Carlo combined with Bayesian to solve some actual problems. So here we have some data, and we made a histogram of that. And we can see it has a rough shape of two mixed normal distributions, and each has different mean or center and different standard deviations. And we try to find out those information out of the data. So using Monte Carlo, we don't need to solve for an analytical solution. So the first thing we need to do is create two clusters, one for each of those distribution, and we make some guess about the probability of about one data point, is that going through the cluster 1 or cluster 2. And then we also make some guess about the mean and the standard deviation of those distributions. And finally, we have some simple result here. This doesn't look bad, but it's just a quick result to further simulate our data and also to see how we are getting closer and closer to the correct result. We create a function with mixed distributions and also all of those initial guess, and then it will finally return a probability optimization function. And here we use Monte Carlo with 25,000 steps, so that will take a lot of time. So I'm not running this cell now, but let's see what we have for the result. So we can actually visualize the traces of those mean values and also the standard deviation values. And we can see they are not converging to some point, but it's actually converging to a distribution of some possible points. And also we can see the converging of the probability goes into the cluster 0. So that's the probability for the first cluster we have. And now we are getting even crazier here. So we took the next 50,000 steps after the initial 25,000 steps, and we also discard the first 10,000 of them because they are not relatively stable, so that doesn't make too much sense to us. And this is a comparison from the first 25,000 steps, and now we have 50,000 more. And notice that the mean values here, or the center of those distributions, they are getting even more converging to some possible range. And next, we are visualizing all of those posteriors. So here is the posterior for the first cluster. This is for the center of the distribution. You can see it's pretty close to our initial guess, or the prior, that is 120. And also we have a standard distribution for that. And those are the posterior for the second cluster. Yeah, we can see it's also close to our initial guess for the center, which is 200. And beyond that, we can also visualize the probability of those two clusters. That is, for a single data point, what is the probability that is belonging to the cluster 1 or cluster 2. And that's why we make this plot, which looks like soldiers from two different countries are fighting against each other. But we can consider the red dots are the probability from the first cluster, and blue dots are for the second cluster. And we can see we have some uncertainty in the middle region. And we can also visualize that in another way. That is, we plot the probability of a data point belonging to our first cluster. So we can see it's pretty certain to belong to the first one at the beginning and to the second one at the end, but we have a sort of combined situation in the middle. So far, we have done Monte Carlo and we've done all the visualization. So one big question before we are getting the actual result is that we have a lot of different combinations of those mean or the center and the standard deviation of those distributions. So how could we choose the best fit out of that? One quick and dirty method is to just use the mean value of those posterior distributions. And let's take a look at the final result we have. The black border are the original data histogram, and this blue and red region are representing our two clusters. And we can see they actually fit pretty good with the original data. And now you have seen how we get those distributions using the Monte Carlo method. And one important thing is that you should not mix those posterior samples because they are from different unknown posteriors. And once you mix them, you are breaking the logic and also the prior assumption. One quick example would be supposed to be have two variables, x and y, and the summation of them would be 10. And if we give them random guess and use the same method to do the simulation, and this is what we have. And let's say we choose x from here and y from there, then the summation of those two might not be 10. And another feature of this model is that we can do the prediction. So let's say we have a new data point that is 175, then we can evaluate the probability that this data point belongs to cluster 1 or cluster 2. And we can also use the autocorrelation to diagnose the convergence of the result. Since usually a high autocorrelation means it's not particularly good, then we can reduce the autocorrelation by thinning the samples. That is, we only keep every second or third sample and we discard the rest of them to reduce the autocorrelation and to increase the convergence. And one last tip for the Monte Carlo method is that you need to choose the priors very carefully, because if you choose a very bad prior, then it's probably you will never get converged in the end. So that is to say that you can use a guess to get it started, but it's going to be a pretty smart guess. Alright, so today I just show you guys one chapter in this repository, and there are a lot of funny stuff, so you can fork and play around with the codes. And if you like this video, please hit like and subscribe it, and also comment down below if you have any questions so we can chat about it. So thanks for watching and see you in the next video.